Welcome back. Now we are going to discuss about the analysis of recursive algorithms. The plan for recursive algorithms based on decide on the parameter indicating an input size, identify an algorithm's basic operation, check whether the number of times the basic operation is executed may vary on different inputs of the same size, set up a recursive relation with the appropriate initial condition expressing the number of times the basic operations executed, and solve the recurrence or the recursive relation by backward substitution or any other methods. For recursive algorithm, we are going to take a simple the Fibonacci series example. So when we consider a Fibonacci sequence of numbers 0, 1, 1, 2, 3, 5, 8 and so on, the simple recurrence that we find is f of n is equal to f of n minus 1 plus f of n minus 2 for all n greater than 1. And two initial conditions that f of 0 is equal to 0, f of 1 is equal to 1. The Fibonacci numbers were introduced by Leonardo Fibonacci solution to the problems about the size of the rabbit population. Here, if we try to apply the method of the backward substitution to solve this equation, we fail to get in easily discernible pattern. Instead, let us take advantage of the theorem that describes the solution to the homogeneous second order linear recurrence with a constant coefficients a x of n plus b x of n minus 1 plus c x of n minus 2 equal to 0. So a, b, c are some fixed real numbers called coefficients of the recurrence, and x of n is an unknown sequence to be found. According to this theorem, this has an infinite number of solutions that can be obtained by one of the three formulas, and which can form the characteristics equations for computing the Fibonacci numbers. Let us look at the simple recursive evaluation for the n factorial f of n. So n is equal to 0, it returns 1, or else n into f of n minus 1 into n. So the the function f is called again with the value of n minus 1, and again n minus 2, again n minus 3. When it becomes 1, when it becomes 0, it returns 1. Usually the stack data structures are the one which is used to solve this kind of the recursive evaluation. So m of n is equal to m of n minus 1 plus 1, and then m of 0 is equal to 0. Let us look at the simple Tower of Hanel puzzle. Is having 3 poles, and pole 1 is having the dice as the bigger one and second biggest, third biggest, fourth biggest, fifth biggest, and the smallest one. Now we have to use the intermediate pole to bring these devices into the third one. So the recurrence number of moves is m of n is equal to 2 into m of n minus 1 plus 1. M of 1 is equal to 1. The algorithm moves like this. n, s, d and temp. If n is equal to 1, move the disk from s to d, source to destination. Move the top n minus 1 disks from s to temp using d. Then towers of n minus 1 comma s, temp comma d. So here we interchange the pole and move the remaining disks from s to d then. Move n minus 1 disks from temp to d using s, towers of n minus 1, temp, comma s, comma d. This is the tree of calls of the tower of Hanel. N calls n minus 1, n minus 1 calls n minus 2, n minus 2 calls n minus 3 and so on. And finally, it calls the first disk, that is a 1. Next example is the counting of bits. The recursive counting. If n is equal to 1, it returns 1, otherwise bin rec of n by 2 plus 1. The number of binary digits in n by n's binary representation. Here the execution time is calculated like this. A of n is equal to a of n by 2 plus 1. So n is greater than 1. So it's become n by 2 will be lesser. A of 1 is equal to 0. So solve using the smoothness rule. This is the way how the execution time is calculated for the recursive functions. Thank you.